Hello. This is the second video of a multi-video tutorial series using the FluCoMa toolkit to make a two-dimensional sound browser to perform different sound slices in a two-dimensional space. In the first video, we analyzed the drum loop using BufOnsetSlice to identify where in this drum loop these different drum hits occur by looking for spectral onsets. And then we took those onset positions and we plotted them to see where they occur in relation to the drum loop. And then we also use these drum slice positions to play back the individual slices using this small function here that'll play back each slice with a 1 second wait time in between each slice. That's just some of them. In total we have 24 slice points, which will be 23 drum slices. So the next thing we're going to do is we're going to analyze each one of these drum slices using a spectral analysis and get the spectral centroid. And then in this video, we're just going to sort these drum slices according to spectral centroid and play them back in order of spectral centroid and then see what that sounds like. So the way that we're going to do this is we're going to again use this indices buffer, which contains the slice points as identified by BufOnsetSlice, and use them in pairs, just like we did to play back our slices, where we will use one sample position as the beginning of our sample, and then the next one as the end of our sample of our drum slice. So start and stop positions. And then the next drum slice will again start here and stop here. Then the next one will start here and stop here. So we'll use those sample pairs to identify the analysis window that we're going to analyze in our source buffer. In order to do that, I'm going to again load these slice points in the indices buffer from the server back to the language. And then I'm going to iterate over these slice points using the method call doAdjacentPairs. And what this will give me is the start position and end position for each of my sample points. So it's going to give me this one and this one as the two arguments that it passes into this function first. And then the next thing it passes into this function will be this value and this value. And then the next one will be this value and this value. So each time it runs this function, it's giving me the next pair of adjacent values. Then it also can give me a counter that I'll just call I here so that I know which slice I'm analyzing. Let's just print that and look at what it reports back. So here we have all of our start and stop points for our slices, and we can see that slice 0 starts at this sample and ends at this sample. And then slice 1 starts at this sample and ends at this sample. And this goes all the way up through the 24 different slice points, which would give us 23 different slices named 0 through 22. And this is because if we think about a buffer that has just 5 slice points, this is a start and a stop, a start and a stop, a start, a stop, a start and a stop. Those 5 slice points will actually give us 1, 2, 3, 4 different slices. So we'll always have 1 fewer slices than we have slice points in our buffer. So the analysis that we're going to use first is going to be the FluidBufSpectralShape analysis. And in order to have this run, we're going to call process blocking. We're going to tell it which server this buffer is on. We're going to tell it the source buffer, which is our buffer called SRC. That is the drum loop that we want it to do the spectral analysis of. And then here we're going to give it a start frame and a num frames. This is going to be the section of the buffer source that it's going to analyze. So start frame is going to be our start position here. And then rather than providing the end sample, we actually need to provide the number of samples from start that it should analyze. So we can compute this pretty easily by just taking the end sample minus the start sample. That'll give us the difference between the two, and it'll give us the number of samples that it should analyze to go from our start to our end. I also need to give it a buffer passed as the argument features, which is going to be a buffer that we're going to use to store the spectral analyses in. So once it does the spectral analysis, it will write that analysis into a buffer, and we'll call that buffer spec. I'm going to make that buffer appear. And then for now, what I'm going to do is I'm going to sync with the server here and look at the contents of spec. I'm also going to just look at what the shape of spec is. So I'll just post spec to the post window, and we can look at what the shape of it is there. And I will move this post ln down here so that we can see the individual slices. So now we can see here that it's analyzing all 23 of my drum slices, 0 through 22. And here's a start position, a stop position. Here is the contents of that spec buffer. And then here is the shape of that buffer. So this buffer has 7 channels, which is good. They all have 7 channels, which I'll show you what they are in just a moment. And they all have a different number of frames in this buffer after each one of these drum slice analyses. But they're ranging somewhere between, here's a short one, 14, 12, up to, 53. So the way that spec buffer gets shaped is like this. There's 7 channels. Each channel contains a different spectral analysis that is provided by BufSpectralShape. And we can see here those analyses are spectral centroid, spectral spread, spectral skewness, spectral kurtosis, spectral roll-off, spectral flatness, and spectral crest. Because the buffer that it's analyzing is just one channel, we get these 7 channels for the 7 analyses. If the buffer we were analyzing was 2 channels, we would get 14 channels in our spec buffer. 7 channels of analysis per channel in the input buffer. The number of frames in spec is going to be the number of FFT frames that are in the slice that we're analyzing. So if a certain slice, and all those drum slices are different lengths, so they'll all have different FFT frames in them. For each drum slice, however many FFT frames there are is how many frames you will have here. So each FFT frame in our drum slice will return all of these analyses. What this means is that in the spec buffer, there are no longer audio samples that you would use to create a signal and play back some audio. Instead, they are these time series of analyses. So the sort of x-axis here, or the frame position, is still a time series, but rather than being an audio signal, it is now a time series of spectral analyses. We're actually interested in only using one of these analyses. We're just going to use spectral centroid for right now. So we're going to tell BufSpectralShape that it should just return for us the spectral centroid. And the way that we can do that is by passing in the argument here, select, and then an array of symbols of which analyses we want it to return. So I'll just put in here centroid, and that'll give me just the spectral centroid. I could pass other analyses in here if I wanted to also have the roll-off. I could pass in here roll-off, and then it would return to me just those 2 analyses. But now I'm going to just ask for the spectral centroid. So now if I run this, I can see that all of these spec buffers, right? After each one of these analyses, the spec buffer has just 1 channel. And that's good. That means that that's just the one spectral centroid channel that it's returning to me. So now spec buffer is 1 channel long, a time series of the spectral centroid analyses for a sound slice, and then it is however many frames long as there are FFT frames in the slice we're analyzing. So this is good. Now we have a spectral centroid description of each one of these sound slices. However, there's still a problem here, which is that what we're going to want to do is sort these sound slices according to spectral centroid. But if we have some sound slices that have 52 FFT frames in them, so 52 spectral centroid values that describe it through time, and some of them have 39 FFT frames, so 39 spectral centroid values. Some of them have much fewer, 14 spectral centroid values. How would we compare them? Well, what we're going to do is we're just going to find the average spectral centroid across the entire sound slice. So the average spectral centroid of these 14 in the time series for this slice, the average spectral centroid of these 48 in the time series for this slice, and then that average spectral centroid is what we will use to describe each of these sound slices and sort them. The way that we're going to do that is we're going to use another FluCoMa buffer processor, which is going to be FluidBufStats. And FluidBufStats is going to let us take some statistical measures of some values in a buffer. We'll call process blocking, tell it which server the buffer we want it to analyze on, and now the source here, the buffer we want FluidBufStats to take the statistical measurements of is going to be our buffer called spec. And here we're going to also pass in a buffer using the stats argument that we're going to write the statistical measures into once BufStats has done the statistical analysis on the values in the buffer called spec. So we'll make a buffer called stats that will have it write those statistical measures into. I better make that buffer. And now what I'm going to do is, after this is done and I sync, I'm going to just check not the spec buffer, but the stats buffer. And I just want to see what the shape of that is. So now what I have here, for each one of these sound slices, I'm looking at the buffer called stats, which has some values here. And we can see that each one of these has 7 frames and 1 channel. So that 1 channel is going to be, again, related to the spectral centroid, just like the 1 channel we had in the buffer called spec. However, the contents of that are no longer going to be a time series of spectral centroids across the sound slice. Instead, it's going to be 7 statistical measures of that time series of spectral centroids, which are all going to be contained in these 7 frames that are in the buffer. FluidBufStats will write these statistical measures in this order for each channel in our buffer that is an input to BufStats. So here we're just analyzing the 1 channel, just the spectral centroid, because we're telling FluidBufSpectralShape to just give us the spectral centroid. But BufStats would do this for however many channels are in the buffer that we pass to it. So it's going to give us the mean value, the standard deviation, the skewness, kurtosis, the low percentile, the mid percentile, and the high percentile, which by default are going to be the minimum, median, and maximum values. So no longer is channel 0 a time series of spectral centroids. It is now a summary of that time series of spectral centroids using these statistical measures. We could do some things with this if we wanted to. We could use some of these different statistical measures in different ways. For this purpose, we're just going to take the mean. We're just interested in the average spectral centroid for each sound slice. So we can actually tell BufStats that we want it to give us just the mean, similar to how we told BufSpectralShape that we want it to give us just the spectral centroid. We'll do that again with an argument select, and then put in a list of the statistical measures that we want it to return. We can see that for each one of these sound slices, after each slice is analyzed, we have a stats buffer that has 1 channel and 1 frame. And that's going to be the mean spectral centroid value for each of these sound slices. And we're also posting that value after we load it back to the language. We're posting that value here so we can see these are all of the mean spectral centroids for each of the sound slices that we analyzed. So now we have the mean spectral centroid for each sound slice. The next step would just be to sort them. So the way that I'm going to do this is I'm actually going to load all of these mean centroids into a buffer, and then once they're all in a buffer together, I will load them back to the language. And this is because currently the value is in a buffer, and I don't want to have to load it back to the language each time I do this analysis. I certainly could do that. That's basically what I'm doing here. But as we do bigger analyses and more batch processing of more sound slices, it'll actually be a lot more efficient if we leave all the processing on the server, store it all there, and then when it's time to do the sorting or do some manipulating of it, then we'll bring it back to the language just in one call. So I'm going to make a buffer here called mean centroids. And then what I'm going to do is, after each FluidBufStats call here, I'm going to call FluidBufCompose. And FluidBufCompose is essentially a buff copy operation. I can just take some values from one buffer and move them to another buffer. So I'll call process blocking, tell it which server this information is on. The source buffer here is going to be our stats buffer, because I want to copy out that mean value that is currently in the buffer called stats. In fact, it's the only value in the buffer called stats. I can leave start frame, num frame, start chan, num chans. I can leave all that alone because there's just the one value, so it's just going to copy that. But if I wanted to be really specific here, I could say start frame 0, num frames 1, start chan 0, num chans 1. But here I'll just leave it as is. And then I'm going to say destination should be my buffer called mean centroids. Now, when it copies this value from stats into mean centroids, I want to make sure that it copies it into the right position. And if I did this, what would happen is it would just copy it into the beginning of mean centroids every time it does the copy. I want it to copy it into a different position depending on which slice I'm doing, right? Which slice I'm analyzing. And I'm counting which slice I'm analyzing here with this counter variable. So I'm going to say dest start frame should be I. And so now each time this BufCompose copies whatever value is in BufStats, right? And it's always just the one value that is in that buffer. So whenever we copy that single value out of stats, it will copy it into mean centroids at the frame that is the index of the slice that we're analyzing. So let me put that there. And now I actually will get rid of all this, and then at the end I will just sync once, and then I will get the contents of this and take a look at it. So we can see now I have 23 values in my mean centroids buffer, which is good because I have 23 sound slices. And I'm printing them out right here. So here are the mean spectral centroids for each sound slice in the order that they occur in the source buffer. One thing I'll point out here about the fact that I'm putting one sync down here, and we'll talk about this in the future when we do some more complex batch processing of sound files, is that the way that this loop is going to work, you'll notice I'm not using any syncs inside of this do adjacent pairs loop here. So what's happening is that each one of these process blocking calls is being sent to the server, and they're all piling up in order on the OSC server queue. So these are happening in order. First, we're doing the BufSpectralShape process blocking analysis for sound slice 0. Then we're doing this for sound slice 0. Then we're doing this for sound slice 0, and copying that mean spectral centroid into index 0. And then basically right after all of that gets sent to the server, this isn't even done processing yet, but this loop is going to immediately send this information for sound slice 1. It's going to send this operation, then this operation, then this operation, and those will go right in the queue, in line, right behind these operations for sound slice 0. And so essentially what we're doing is we're taking all these operations, these 3 process blocking for the 23 different sound slices, and stacking all of those operations up in a queue on the server, in the OSC server queue, so that as the server gets done with each one of them, it just goes to the next one in the queue until eventually it has processed all of them. This sync operation then I'm putting at the very end, right after we do the loop and send all of these jobs. Then there's a sync that I put right here, so that's at the very end. And then once we get through all of those jobs, we get to the sync, we sync with this, and then we continue on here and load those values back to the language. So now what I'm going to do is I'm going to get all of these mean centroids back to the language, which I'm doing right here, and store them in an array, because then I can sort them in that array. So I'll say mean centroids equals fa. Fa here just stands for float array. So now if I run this, and then go down here and just print this, we can see that there are my mean centroid values. Now what I want to do is I just really want to know what order these would go in if I were to rearrange them and sort them according to mean centroid. So what I could do is I could just say .sort, and it'll give me them in order, right? Here's the lowest, which is 1,000, then which is 1,300, 1,400, 2,200, 2,200, 28, etc. But what I actually want to know is the order that they would go in, because then I can use that order to play back these sound slices. So there's another call I can make, and that would be order. And that'll give me the order of indices that would rearrange this array so that they are sorted properly. Now if I do this right now, it's going to say that everything is in order because I just sorted it. So I need to run this again and then call .order, and now I will have these in the order in which they should be sorted in order to sort them according to spectral centroid. So first I should hear the 15th or index 15 sound slice, then index 17 sound slice, then index 18 sound slice, then index 20 sound slice, etc. And if I do that, then I will hear them in the order that they would be if I sort them by spectral centroid. So what we can do now is save this, and then just take a look at it. And then what I want to do is I want to loop over this and play those sound slices. So we've already really done this, right? We did that right here, where we looped through the values and just passed that slice index to our function called playSlice, and it played that slice for us. So I'm just going to take this, put it down here, but instead of getting the indices in order, what I want to do is take this order and pass it into here. And now what I can do is just play them back in order using this index. And what we can hear is that these slices are roughly sorted by spectral centroid from sort of darkness to brightness, maybe from kick drum to cymbal. However, of course, we also hear some things that sound out of order, which raises some questions about, like, well, what are we really analyzing here? What are the values that we're really getting? So if we think about, first of all, spectral centroid, right? So it's a sort of measure of center of the spectrum of a sound. If we have a sound slice where there is some kick drum as well as some hi-hat happening at the same time, well, our spectral centroid is going to be maybe somewhere in the middle, right? Not as low as a slice where we had just kick drum, or not as high as where we had a slice just cymbals. So that's one thing to keep in mind. Another thing to keep in mind is that we're taking the average over the entire slice. So even if in a certain slice there's some kick drum at the beginning, maybe some cymbal at the end, even that is going to give us something in the middle, because we might have some low spectral centroids at the beginning of the slice, then some higher spectral centroids at the end of the slice, and the average might end up somewhere in the middle. So as we listen to these, it's important to reflect on what we're hearing and really think, why are we hearing it ordered this way? How might we have it be ordered more aligned with the perceptual ordering that we want to hear? So a couple things we could do is we could try to make smaller slices. Let's try lowering the threshold here to 0.1. And now it's going to give us 36 different drum hits. Let's try to lower it even a little bit more, maybe 0.05. We have 42 drum hits, so that's going to be a lot of them. They're going to be much shorter than we had before, about twice as many. Here they are in samples again. We can peek at them here, so we have a lot more slice points there. And now if we go down here and do the analysis on all these drum slices, and then find the order of them, and then play these back, we have a lot of kicks at the beginning, now some snares in the middle, and we'll see if we get more cymbals at the end. So a lot of cymbals at the end there. There's a lot of places in this drum loop where there's both kick and cymbal at the same time. We seem to get those at the end mostly, which were these ones right about in here. So in the next video, what we'll do is we'll take these drum slices and we'll add another analysis to this. We'll take the spectral centroid and the loudness, and then we'll use those two together to plot them in 2D space.